Okay, quick summary. Vertex form of quadratic function, here's your vertex form. Why is it called the vertex form? Well, let's take an example. Okay, this example, I'm going to make a table that's going to reveal, I hope, why this is a vertex. Okay, so I'm going to use x values that are centered around the value that makes x minus 3 0. Okay, that would of course be where x equals 3. So x equals 3 is in the middle. And then I use my -2, -1, -1 half, 0, 1, 2, 1 half, 1, 2, and I add those to 3. Okay? And my table was wrong. I should have 1 here and 2 here. Okay. So when I add -2 to 3, I get the 1. And then I add -1 to 3 to get this and so forth. So if I subtract 3 from all these numbers, I get my -2, -1, -1 half, 0, and so forth. Which means that I'm going to get the same numbers I get from my basic x-squared graph, or x-squared table. So the familiar 4, 1, 1/4, and so forth. Then if I multiply those by 2, I get these numbers. That kind of corresponds, incidentally, to vertically stretching these numbers by a factor of 2, right? And then I add the -5, and I get these numbers. Okay? So that the lowest number we get here, the most extreme number, is the one I get when x equals 3. Gives me -5. All the other numbers are greater than -5. All the other points that we get would lie above the point 3, -5. So that 3, -5 has the lowest y value, and we know that then when that's the case for a quadratic function, that is the vertex. So this is kind of an explanation of why HK is the vertex. Okay? So the lesson is the x value that makes x minus h squared 0 gives us the vertex. And of course the y-coordinate of the vertex will then be k, because whatever number makes the x minus h 0 makes all this 0, and you're left with k. And now we're going to check to see if that's really the vertex using the procedure we already know very well with the quadratic formula. So first we expand this. Okay, so we take this thing and we expand it, except I screwed up here, and I put a +5 instead of a -5. And we didn't get what we expected, but then we did it right. And this is still worth seeing. Okay, here's the process. We expand this, use a distributive law to square this, we get this, multiply through by the 2, and collect terms, we get this. We get zeros. Well, to get the zeros, we do the quadratic formula, finally we get a negative square. We don't have zeros. The axis of symmetry is that x equals 3, and the vertex would then have the coordinate we get when we plug in 3 for the value of x. And in this case, that would of course give us, that ends up giving us 5. We put in 3 into this form of the function, we get 5. Now that doesn't agree with the vertex we got here, because I wrote down a +5 instead of a -5. So I now ask the class, okay, do it the way it should have been done with the -5. And of course we expand it, we get this, very simple. Then we get the vertex still at 3, and then we plug that 3 in to get the y-coordinate of the vertex, plug it into this form, and we get 2 times 3 squared minus 12 times 3 plus 13. Work that out yourself, gives you -5. And incidentally, the zeros are approximately 1.4 and 4.6. Okay? Then we went ahead and did this example. We did the usual thing to find the axis of symmetry. Quadratic formula gives us the zeros and the axis of symmetry. Then we plug the coordinate of the axis of symmetry in here, and we get the y-coordinate of the vertex. So our vertex form is going to be the negative a times x minus h quantity squared plus k. The h is the 1.5. The a agrees with the a up here. And there it is. And then there's our vertex form. Our vertex is 1.5, 8.75, just like it was up here. And then we check by expanding this, and we get back to the original. Now, another thing that we have here, f of x is x squared minus 2x. So, for example, f of 3, x has been replaced by 3, so replace all the x's by 3, and we get 3. Okay? Now, f of a would be what? Well, what we do with function notation is whatever's here replaces x. You know, it replaces x, as we did. X has been replaced by a, so we replace every x by a, and we get a squared minus 2a. F of b, well, we replace every x by b, and we get b squared minus 2b. Okay, then, I have a little trouble with this. F of a minus b, well, we're replacing all the x's with a minus b. We don't have to do any arithmetic with that. We just plug it in. Then we can do a little algebra if we need to. But we just replace every x by a minus b, so that x squared becomes a minus b squared, and negative 2x becomes minus 2 times the quantity a minus b. Now, if we do f of a minus f of b, we get something that's actually pretty much different. Not totally different, but it is a different expression. Because function notation doesn't distribute over addition. It's not a distributive law. There's no distributive law that acts on function notation. F of a minus f of b is just what? Well, f of a is, we found it here, a squared minus 2a, but if we just had this, we'd say, okay, f of a, x has been replaced by a squared minus 2a. Now put parentheses around this, just because that's one chunk of it. That parenthesis is more or less optional. F of b, well, replace the x's by b, we get b squared minus 2b. Okay, now then we can do a little arithmetic with it and really show the algebra, and really show that these terms, or these expressions aren't exactly the same. Okay? And the difference is simply that we don't get the 2ab. This is here, it's not here. Every other term here is down here, but the 2ab isn't. So it's very clear that these are very different expressions. They're not all that different, but they're different. Okay, so there it is.